So in the last section, we talked about the integral as being the shaded area under a curve. And now we're going to talk about turning that into an area function, which will give a general formula for finding the value of an integral starting at a fixed value of a on the x-axis, and then extending as far to the left or to the right as we'd like. So we're going to allow x to be a variable here that the area function depends on. So here's the definition. Let f of t be a function and a any point of its domain. For any input x, the area function a sub f is how we read that, is defined by the rule a sub f of x is the integral from a to x of your function f of t dt. Now the reason we switched to f of t dt here is because we're already using the variable x in the area function. So this is just saying that the area function is the signed area defined by the function between the values of a and x. And this makes more sense if you're looking at this picture here. And notice in the picture, we have our function in terms of t, and a is a fixed value, the lower limit of the integral. And we want to come up with a formula that will work for any particular x value that we allow x to take on. So here x might be 3. We want the area function to calculate what the area of this shape is. If we were to move x to the right and create a larger shape, we want the area formula to calculate, when we plug that new x in, the expanded area. So that's what this next paragraph here is describing. This next example is a modified version of example 1 and 2 from the textbook. We're going to let our function in this case be f of x equals 3. This is a constant function, which when you graph it is just going to be a horizontal line going across the graph at 3. So first we're going to begin by sketching a graph of the area function. A sub f of x is going to be defined this time as the integral from 0 to x. And what that's telling us then is that this 0 is our a value. That's the fixed place where the shape under the curve is going to start being created. Again, we're going to allow x to be a variable, and we're going to use our particular function, but using it in terms of t instead of x. So I want to graph this for positive inputs of x as a shaded area. So I begin by graphing my function as a horizontal line at 3. I'm only worried about letting x take on positive values, so I'm going to stay to the right of the x-axis. So this is my function. My a value is 0. So this right along the y-axis is the beginning of my shape. And now I want to expand so x can be any value. If x was 1, it would be this little rectangle that would be created. But I want to let x take on any value, so I'm just going to go somewhere out here, kind of put a dashed line to remind you that this side can move and change, and I'm going to label that x. So if I shade in this area, that's a graph of the area function. Next, I'm supposed to write a formula for the area function for these positive inputs of x. And then on the next graph, I'm going to sketch a graph of that function. So this shaded area is my area function. So what shape is created by this function? Well, it's a rectangle. So I'm going to be using the area formula for a rectangle to write my area function. And of course, it's length times width. Now, the length of this rectangle, if I call that the bottom side, is going to change in size. As x is bigger, it takes on a bigger value. As x moves smaller, it's going to be smaller. So I can't say that my length is 2 or my length is 3. My length is going to be represented by a variable, which is x. And my width is fixed because this is a constant function. The width is always 3. And so a formula for my area function for the area under the curve is going to be 3x. Now I've added here a little note that this area function is 3x when your original starting function was 3. Obviously, if your function was different, it's going to create a different area function. And there is a relationship here that we'll come back to. Now that I have my formula for my area function, I can just construct a table of values, my input being x and my output being the area. And I'll just pick some x values. Now I'm going to stay with the positive inputs for the time being. So I'm going to choose things like 0, 1, 2, 3. 0 just gives me a nice starting place. Then 3, 6, 9, and 4 would be 12. So I plot those points. So you can see I've taken those points and plotted them, and now I have a line. This line represents, for each input x, the corresponding output by the area function. What does this predict about the negative values? The next question says, does the formula you wrote also make sense for negative inputs? Well, what would it predict? If you put in an input of -1, -1 times 3, just substituting into the area formula, is -3. And -2 would be -6. And you can see that does follow the pattern of the line. -3 would be right down here. Does the formula give the correct area? It's telling me that if my input is -2, my area is going to be -6. First of all, remember that areas can have a sign when we're working in calculus, as we've talked about. So I'm going to use this last graph to kind of think about whether these answers that the table is generating from the formula make sense. I'm going to begin by sketching my original function, my constant function. Suppose, we can test either one of these, but I'm going to let x equal -2. So what shape does that create? Well, again, going back up here, the area function is defined with a fixed starting point at 0. So one edge of my shaded region should be right on the axis. Suppose x is, for instance, -2. If it is, I'm going to sketch my little dotted line here, and hopefully you can recognize that, again, I've got a rectangle here. So what is the area of this shaded region? Well, the area function, when we input -2, is going to follow this rule right here. So I'm going to substitute in -2. So it says the area function, when x is equal to -2, will be the integral from 0 to x, 0 to -2, of my function f of t dt. Now, in the previous section, we talked about when your upper limit is actually smaller than your lower limit, that's equivalent to taking the negation of the integral with switched limits. Okay, so I do that. So this says my answer for -2 should be negative, whatever the area would be from -2 to 0. So if I'm reading from -2 to 0, I'm reading left to right again. So I'm going to do length times width. I've got the negative sign in front. The length is 2 units. When we're reading left to right, it's just a +2. My width is 3. So notice I get -6. So it turns out once you have an area function created, that formula will generate the actual value for the shaded area for any positive or negative inputs. All right, we're going to look at another example. Now, this one's not in the book. I wanted to change the questions up a little bit. So we're given a new function. We're going to try to create an area function that'll be a general formula for allowing x to take on any value. And we're going to begin by sketching a graph. Okay, so just like in the last example, we're going to need to start by taking our function and graphing it. Now, you should recognize, and I'm putting t in here again because we're going to use t's instead of x's. You should actually recognize that this is a line. However, if you're a little bit rusty with that stuff, you can always just plug in values and figure out what your output is. I don't need to limit myself to positive or negative. It's going to work with either. So I can start with a negative value like -1. -1, when you substitute for t, -1 plus 2 is 1. And from there, you can kind of see the pattern. So I'm going to go ahead and plot those points. Here is my graph of my function f of t. When I read the area function, it's equivalent to an integral starting at 2. So once again, this 2 is my fixed side of my shape created under the curve. So I'm going to draw that as a solid line at 2. And then I want x to be any input. So I'm going to choose kind of some general random place. I like to use a dash line just to remind you that x is flexible. It doesn't have to stay in this position. And I've now created a shaded area. So here is the area function. Now I want to write a formula for this one. So once again, because this is a standard polygon, we're going to recognize the shape. In this case, it is a trapezoid. Because it is a trapezoid, the area function will be based on the formula 1/2 height times the sum of the bases. This will be equal to 1/2. Now remember, the bases are the parallel sides, so the height is this distance here. Now, if it was just 2 to 3, obviously the height would be 1. If it's 2 to 4, it's 2. If it's 2 to 5, it's 3. What if it's 2 to x? Well, what we're actually doing, if you think about it, if it was 2 to 3, we know that it's 1 unit, and we get that mathematically by taking 3 and subtracting 2, or taking 4 and subtracting 2. So the height we're going to represent in terms of x and say it's x take away 2. Base 1 is based on the fixed edge, so this has a fixed length. It will always be 4. Base 2, if you notice, is going to become longer if x moves to the right. It's going to get shorter if it starts moving back to the left. So the length is actually dependent on x. So how do we know what the height is going to correspond to? Well, remember, if x is the input, this function outputs x plus 2. So if x is my input, the length of this base will always be equal to the output of the function, which in this case would be x plus 2. Now, once you have that done, you've got to do a little bit of algebra here after you simplify the second set of parentheses. And once you get to this step, I would recommend that you multiply out these two binomials first and then distribute the 1/2 in afterwards. So we're using binomial multiplication. X times x is x squared. X times 6 is 6x. Negative 2 times x is negative 2x. And negative 2 times 6 is negative 12. Combine your middle two terms, and we're looking at 1/2 times x squared plus 4x minus 12. And if we distribute the 1/2 through, we'd have 1/2 x squared. Half of 4x is 2x. Half of negative 12 is negative 6. So this is the formula that will generate the value of the area, which is the integral, for any input x. To sketch the graph of this formula, you again should recognize the shape. It's a power of 2, so this is going to be a quadratic. I'm going to just go ahead and make a table of values for this function as well. So in the interest of time, here's what the table turns out to be. And how I arrived at these numbers is I took some inputs like x equals negative 3, substituted into the area formula, and calculated the output. So I'm going to go ahead and graph. All right, I have sketched the graph, which you can see has that parabolic shape. I've also written the sentence that connects the function to its area function. When your starting function is f of x equals x plus 2 and you allow x to vary, the value of the area will be generated by this formula. So the last thing that I'm asked here is, what does a sub f of 4 mean and what's its value? So I'm going to put in a 4 here. Remember your original definition of your area function. So I'm being asked, what is a of f of 4? Well, if I substitute it, it's telling me it's going to be equal to the integral from 2 to 4 of f of t dt. And remember, this integral represents the signed area between my function f and the x-axis from 2 to 4. The area function is the signed area, the area between the function and the x-axis from 2 to a particular x value, which in this case, the input is 4. So from 2 to 4. So that's the meaning. And to figure out what its value is, I would just go ahead and substitute 4. If you do the math on that, you will get an output of 10. So a sub f of 4 is actually 10. All right, we're going to finish up with one last example. This is also not in the book, but it's similar to the exercises that I assigned. I'm going to have an area function here defined by a starting fixed value of 1, allowing x to vary for a particular function, which is the function on the graph below. We're going to use this graph to answer the questions. Part A says, which is larger, a sub f of 5 or a sub f of 2? So let's think about what these mean. A sub f of 5 is the integral from 1 to 5 under this curve. So the integral from 1 to 5 represents the signed area from the x-axis to the function. I'm going to go ahead and shade that in. This shaded area then represents the value of the integral, which is the area function with an input of 5. Notice that this is below the x-axis. So I know that this is going to be a negative value because areas below the x-axis are always negative. Now I'm going to go ahead and figure out what a sub f of 2 would be. Well, that's the integral, but only from 1 to 2 of f of t dt. I'll shade in that one. All right, this shaded region is also located below the x-axis, so it will also have a negative value. All right, I've put the blue shading back for a sub f of 5, and you can see I've now created sort of a purple where it overlaps with a sub f of 2. So the question is, which is larger? And you may be tempted to want to say that clearly the blue shading is larger, so therefore a sub f of 5 would be the larger value. However, please keep in mind that these are negative numbers that we're working with. So to make things a little bit clearer here, instead of working with these shapes where it's very hard to calculate in their areas, I've kind of simplified the picture to 2 rectangles that are below the x-axis. This little red guy, which is approximately the size of this purple shaded area here, and then the blue rectangle. If I calculate these areas, the red rectangle has an area of length is 2, width is 1, and it's below the x-axis, so it's negative 2. The blue rectangle has a length of 4 and a width of 2, and it's below the x-axis. So you can see I put negative signs on both of these. Now, technically, which of these numbers is larger? Well, hopefully you do know that negative 2 is bigger than negative 8. So even though the area looks smaller, because these are signed areas, that signed area below the x-axis is bigger in terms of its value than the blue signed area. So that means my final answer is a sub f of 2 is larger. All right, for part B, we are asked, is a sub f of 11 bigger than 0? Justify your answer. Again, I would recommend going back to the original statement of the shaded area as an integral, and I'm now going to create that on this graph. Okay, so I've got my fixed side of my shape, and if I let x go from 1 up to 11, that's going to incorporate this area, 1 to 5, as well as this area from 5 to 11. Now we're asked, is a sub f of 11 going to be a number that is bigger than 0? Numbers bigger than 0 are positive. So if you were to compute the signed area, you would total up the area that's underneath the x-axis together with the area that's above the x-axis. And really the question here is, which is there more of? Is there more area above the x-axis or below? Clearly there's more above. This function actually is symmetric. So we've got more area above. So if you have a positive number for this area and a negative number for this area, the end result will be positive. So a sub f of 11 will be greater than 0 because even though the area from 1 to 5 is negative, the area from 5 to 11 is positive and larger. When combined, the result is positive. Now there's one additional thing here that I sort of skipped over, which is this sentence in the middle. At this point, it's worth mentioning that the area function a sub f, which represents the signed area, is also known as an antiderivative of f. So going back to this first example here, what we're saying is that this area function of x was 3x when f of x equals 3. Or in other words, when f of x equals 3, the antiderivative is 3x. So this again has to do with that idea of trying to reverse the process of taking the derivative. All right, so the focus of this section was on the area function. I've assigned a few exercises for you to try.